Hello everyone, welcome to part 2 of our webinar on cost functions when it comes to artificial intelligence. This was our agenda. We discussed about cost functions, primer, how do we measure the cost function or error function or loss function, all mean the same. When it comes to output variable, which is continuous, then if discrete output variable exists, which is binary in nature, then how do you measure the accuracy or error? How do we handle multiple discrete output? Then entropy and cross entropy. We have discussed until what if output is discrete in multiple categories. I mean, we were discussing about cross table calculation and confusion matrix. And then we were supposed to discuss these two. We discussed at a high level about what do you mean by training data, what do you mean by testing data, and we discussed also clearly that we will have a 4-hour session on entire project management overview of data science or AI projects. That is when we'll discuss in further detail of validation for validation data, etc. And then we discussed about these. If the output variable is continuous, you can measure the error using mean error or mean absolute deviation or mean squared error, root mean squared error, mean percentage error, mean absolute percentage error, so on and so forth. Error percentage plus accuracy percentage should be equivalent to 100%, and accuracy plus error should be equal to 1. Either of these can be used. Then we discussed about discrete output variable when you have binary data, and how do we measure not just the overall accuracy but precision, sensitivity, specificity, F1 ratio, so on and so forth, precision, recall, and all that. Then we have also discussed about the ROC curve, how to interpret that, etc. In our previous webinars, we have also discussed about how to manually, using an Excel, calculate these values and plot this. And then we have also discussed about cross table calculation. And one thing that we were supposed to discuss here was cost of misclassification. We need to not just look at how many of the classifications are incorrectly classified and how many of the misclassifications have been correctly classified. We don't just look at these. Sometimes we go ahead and also look at the cost associated with each incorrect classification. Basically, I mean, there is no cost associated with correct classification per se, but if the reality was false and you have classified as true, then there will be some cost associated with it. If the reality is true and if you have classified as false, then also there will be some cost associated with it. Okay, let us discuss about this example of earthquake prediction. We have positive class and a negative class. When do you say it's positive, something is tested positive? When you have disease, right? For example, you say that you are tested positive. In that way, when we say positive, that means earthquake would occur. Negative means no earthquake will occur. Then you have true and false cases. When we say false positive, that means we have incorrectly classified the positive scenario. That means you classified or predicted that there would be earthquake. The moment you predict that there will be an earthquake, what will happen? Your government would kick in the disaster recovery team. They would evacuate the people. They will create makeshift camps. They will transport all the important equipment to other locations, to safer zones. All these preventive measures which have been taken will cost you, and the cost associated with that is cost of preventive measures. Say for a specific earthquake in a region such as say Hyderabad, for example, it is going to cost you $1 million to evacuate people in a certain locations. Assume. Then you also have to look at false negative costs, right? For example, if you are incorrectly classifying that there won't be any earthquake, what does that mean? That means there will be earthquake in reality, but you have incorrectly classified that there won't be any earthquake. What will happen then? You sent an alarm that hey, there won't be any earthquake, and in reality, if earthquake occurs, then buildings will collapse. There'll be a lot of debris, loss of life, loss of property, and then you have to recover all that by you know kicking in your disaster recovery team once again. So that's a cost. There is a cost associated with that. Say the cost associated with that is $10 million. Then how do you actually calculate the overall cost? Overall cost is nothing but the cost associated with, I mean, this is a cost associated with incorrect classification, right? So cost associated with false positive, which is 1 million, multiplied by how many such instances were there wherein your model has incorrectly classified, plus what was the cost associated with false negative cases. In this case, it's 10 million, multiplied with how many cases were there in your test data when you tested it, which was falling under false negative. When you solve this, you get the cost, overall cost, right? So that is how you look at the cost associated with an earthquake occurring or not occurring. Now, what do I do with this? Apart from knowing the cost, what else can I do? When you sample your data, of course, simple random sampling is the best. However, when the cost of misclassification of positive and negative is different, then you need to do some kind of weighted sampling. What does that mean? You look at which scenario is more dangerous, false negative. So you'll ensure that you have a lot of uh, earthquake cases. So if there is an output variable which is earthquake and no earthquake, your model should learn a lot of earthquake cases so that it does not incorrectly classify, so that it classifies correctly whenever there is an earthquake in some sense, right? So for every one instance of no earthquake label, you need to have 10 earthquake instances so that your model learns more of earthquake instances. All right. So that means if you have one row, then there should be 10 rows pertaining to this. So you're in some sense making your data imbalanced data by ensuring that 90% of the records have earthquake instances and 10% of the instances have not earthquake rows, basically, right? Labels, or rather labels. So this is how you need to make your data imbalanced and then build your model on top of that. Are you guys able to hear me? Can you please use the chat window and confirm, because I just got a message that I'm not clear. Okay, perfect. Perfect. All right, then let me move ahead. Right? So now we need to discuss about entropy, information gain, and cross entropy. We need to discuss about all these three. Information gain is pretty simple. This comes under decision tree. Of course, it can be used as a separate topic altogether, but usually people use it with decision tree. For example, if you have say 100 variables And if you are asked to build a model, you might feel that if you use all the 100 variables to build a model, it might become complex, is what you might feel, right? X1, X2, X3, in that way you have 100 variables. If you use all 100, maybe you might feel that your model might become slightly complex. And according to Occam's razor or principle of parsimony, simplest of the model is the best model. So what you might want to do is, you might want to look at what is the information contained in each and every variable. What is the information contained in each and every variable? Say that is what you want to do. And you wanted to find information gain of all these variables, and ultimately you figured out that, you know, 20 of these variables capture 80% of information. So you will rather include only those 20 input variables which has maximum information gain in it. And then we have cross entropy. We'll discuss these in a bit from now. Okay, so just hold on to your questions, friends. I'll take your questions towards the end. Otherwise, I might miss out. There are too many messages coming my way. Okay, this is a very classic textbook example which we are going to discuss now. This is also part of our regular data science training. You all, people who have undergone the regular data science training, must be aware of this by now. So here we have an output variable. It is a two-class problem. Will a ball be useful for play or not? Simple. And you have three features or three inputs or three variables: ball size, ball color, and price. We want to now understand on which variable has maximum information in it. If there is going to be a variable which has maximum information contained, that means it has no error. And entropy is a form of error. That means entropy should be 0 for those variables which have the highest information. So let us take first ball size and assume that we are using decision tree. It's a two-class problem, so you'll have two decisions. On one side you'll have a yes, and another side you'll have a no. But what is the decision that you will take using ball size which will classify the output variable as yes or a no? For this, if you look at the data, you might feel that, okay, my classification rule would be less than or equal to 50 on the left side and greater than 50 on the right side. Meaning, if the ball size is less than or equal to 50, you're saying that it will be useful for play. If the ball size is greater than 50, then the ball would not be useful for play. Simple. Let us look at the left side. What is the actual value? 10. Ball size is 10. 10 is less than or equal to 50, right? If the ball size is less than or equal to 50, what will your decision tree predict? It will predict or classify that, yes, it will be useful for play. And what does your actual value say? Actual value also says yes. Is there a match? Yeah, but there is a match when you compare. Then let's move on to the second record. Ball size is 1. 1 means it's less than or equal to 50. If it is less than or equal to 50, your model will predict or classify that output variable is yes. And what does your actual value say? Yes. So you compare these two. Is there a match? Yes. Then move on to the next row. 50. Ball size 50, is it less than or equal to 50? Yes, it is less than or equal to 50. Then what does your model predict? It will predict or classify that it's useful for play. And what does your actual value say? Yes, useful for play. Is there a match? Yes, there is a match. Now, let's go to row number 4. Ball size is 100. Ball size is 100 means it's greater than 50. It follows this classification rule. then what does your predicted value say here? No, it won't be useful for play. And what does your actual value say? Not useful for play. Is there a match? Absolutely, there is a match. Let's look at the last record here. 1000. Is ball size 1000 greater than 50? Yes, it is greater than 50. Then what does your classification model say? It will say that prediction is no, not useful for play. And what does your actual value say? No, not useful for play. Is there a match? Oh, yes. So when I choose ball size, there are no mismatches. There are no misclassifications. Okay. Now, let us take another example here. It's again the same thing. Let me take a different color. Now we are going to use price as the other variable. Now here, by looking at this data, you need to come up with some logical decision rule, right? And say your model comes up with this rule saying that less than or equal to 5, it will be useful for play. Greater than 5, it will not be useful for play. Simple. So look at this 5 here. Is this 5 less than or equal to 5? Yeah. So what does your classification model say? Yes, it will be useful for play. What does your actual value say? Yes. Is there a match? Oh yeah. Look at the second value, 2, second row. Price is 1. 1 is less than or equal to 5. Then your model will say it is useful for play. Actually, it is useful for play. Match. Next, 5. 5 is less than or equal to 5. That means your model will say it is useful for play. Your actual value also says useful for play. There is a match. Look at the fourth record. Price value is less than or equal to 5. Then predicted value would be yes, it will be useful for play. But what does the actual value say? No. That means there is a mismatch. There is error. And finally, let us look at the last one, 10. 10 is greater than 5. Then your model will say not useful for play. Your actual value also says not useful for play. There is a match. But there was one mismatch here. Everywhere it worked well, but here it didn't work well. So in comparison to ball size, or in comparison to price rather, ball size has more information in it because there were no misclassifications. If there are no misclassifications, that means your error or entropy value will be equivalent to 0. Wherever you have misclassifications, you'll have certain entropy. All right, this is the underlying logic. Now let's calculate quickly. This is a formula for entropy, right? So first thing is, even before you take such a decision rule, even before you split the tree, you're going to look at what is the entropy in the overall data set. Entropy before splitting the tree or before building a model minus entropy. What is a entropy after splitting the model? And this after part, right, you have to do it for each and every variable. You have to do it for ball size separately, ball color and price separately. You have to do. Say you're choosing ball size, right? When you choose ball size, you will have a left hand side and a right hand side. Left hand side and right hand side. Okay, and then you use some rules. Say you're using less than or equal to 50 here. This your model will figure out, okay, on what should be the values. Greater than 50. This is the rule that you're coming up with, right? So when you split your tree using ball size variable, then you have to calculate entropy for the left side separately, and you have to calculate entropy for the right side separately. After calculating these two, you need to add these two and you get entropy after. You add these two and then you'll get entropy after. Then what you do is you subtract entropy before and after, which will give you nothing but information gain. How much information is available in each and every variable? That's what you'll come to know. This is the underlying formula that you have to remember in basic English terms, right? Information gain is entropy before minus entropy after. Entropy after, for each and every variable you have to do that. And when you have a two class problem, you'll have a left and a right. So for you need to calculate entropy separately for left and entropy separately for right. When you add these two, you'll anyways get entropy after. Subtract it from entropy before and then you get information gain. Okay, now let's proceed further. Let us first calculate entropy before. Okay, it's a two class problem. So how do you write this formula? Minus is because error, right? Error you're representing in negative. So two, you have two classes. So instead of n, you'll put 2 p of xi into log of p of xi base 2. Right? If I substitute I equal to 1 in this formula, you get p of x1 into log of p of x1 base 2 minus, because you have a minus sign. If you substitute I equal to 2, p of x2 into log of p of x2 base 2. Now, this is how we solve it. It's a two class problem. So how many times, it's a two class problem. P of x1 is nothing but p of y, which is nothing but you have 3y out of total 5. So it'll be 3 by 5. P of x2 is nothing but p of no, because it's a two class problem. Probability of no is nothing but I have 2 times no out of overall 5. Proportion or probability in this sense means the same. Okay, so let's write it. Minus 3 by 5 into log of 3 by 5 base 2 minus, that's what I substituted here. P of x2 is this 2 by 5 into probability of 2 by 5 base 2. When you actually solve this, you get this. When you actually solve this, you get this. Okay, it's already calculated. If I were to double click on that, then you see that it's the same thing that I've given there. Base 2 comma 2 means. Okay. You have that. So you have entropy before, which we calculated. Now what do? We calculate entropy after. For that, I think I'll have to erase these things. And these things also. This is 2. Okay. Now let's calculate entropy after. In entropy after, you need to first calculate entropy left and then right. So let's take the left portion first. Left portion is less than or equal to 50. Which portion is less than or equal to 50? Let's see, less than or equal to 50 is 50 and above, right? So this region. Okay, this region above is less than or equal to 50. How many entries are there here? 3 entries. Okay, and it's a two class problem, mind you. So probability of yes would be, how many times do you have yes out of these 3? Because we are referring to only these 3 records. That's the left portion. You have 3 yes out of 3. And how many no do we have? 0 no's out of 3. Because 3 because we are only referring to the left portion. Now 3 by 3 is 1, 0 by 3 is 0. So you say minus this p of y, that's x1, 1 into log of 1 base 2 minus p of x2 is probability of no, which is 0, 0 into log of 0 base 2. 0 into anything is 0, and log of 1 is also 0. Log of 1 is also 0, right? So you'll get overall 0. So I got entropy to the left as 0. That's what is given here. Entropy towards the left is 0. Now let's solve this for the right hand side. This portion, right side. Right side is greater than 50. Greater than 50 is these two, right? Ball size greater than 50 are these two. You have only two. Okay, so let's solve it. How many times do you have yes? 0 times out of 2. How many times do you have n? 2 times out of 2. So here you get 1, here you get 0. So when you substitute that, what do you get? Minus p of y x1, that's 0, 0 into log of 0 base 2 minus 1 into log of 1 base 2. 0 into anything is 0, log of 1 is also 0, so 1 into 0 is 0. So overall you'll get once again 0. Towards the right hand side also you would get 0. Look at that. Once you get left and right side as zeros, you have to add them up. Once you add entropy left and right, you'll get entropy after. However, the challenge here is, let me erase these things. Or the incorrect thing here, or we should not be adding directly. The reason being, when you looked at the left side, there were 3 rows, 3 items, and on the right side there were 2. So it's kind of imbalanced. Hence, you take the weighted sum of these two to get entropy after. So since on the left side you have 3 out of 5, you say 3 by 5, multiply it with entropy on the left side, plus on right side you have 2. So you will say 2 out of 5 were on right side, multiply it with entropy on the right side. When you do this, then in some sense you are taking care of the number of rows or records that you have considered to calculate the entropy. Right, so that's what we will look at now. Friends, I request you to refrain from asking me questions until I complete this, because I'll not be able to see your questions at this point of time. Sorry, but I'll certainly get back to your questions. Okay, so it's 3 by 5 into entropy on the left plus 2 by 5 on the entropy on the right. But anyways, 3 by 5 into 0 plus 2 by 5 into 0 will give you 0. Right? And how do you get information gain? Information gain is nothing but entropy before minus entropy after. Entropy before you got some value, after you got some value. Now if you look at this, entropy after is 0 when you have chosen ball size, because there was no misclassification when you use ball size, and when you have taken decision to segregate as less than or equal to 50 and greater than 50, there were no misclassifications. That means there is no error. Of course, that's the reason why you have error as 0 or entropy as 0, and you get the information gain. What that also means is, if you can split the ball size feature, I mean, if you can use this ball size feature and split your tree, then there will be 0.97 bits of information in your model. That is the interpretation part. Okay. Now I think I'll have to look at the questions. Can we use entropy on regression model? If you are saying that if you want to calculate this when your output variable is continuous, then I think no, that's the answer. Then I think money, I answered it, right? So that's why I was asking you to just hold on. Right, because it's a pure region, that's the reason you do not have any issues. Yeah, recording is going to be made available to you guys. Okay, now back to our discussion. We are going to put this recorded video on YouTube channel, and then we are going to share the YouTube link on the groups. Okay, entropy is clear, information gain is clear. Then what is this cross entropy? Right, this is what we need to discuss now. Let's discuss. Say, usually, I mean, when you have image classification kind of a model, etc., it comes in very handy. And in deep learning, in the loss function, we define binary cross entropy as a loss function, or categorical cross entropy. When you have a binary output variable, binary classification, binary discrete as output, then you use binary cross entropy. Otherwise, you use categorical cross entropy. This is what you use otherwise, right? So why do we use this? What is this? Let us understand. Okay, here what we define is Q and P. P is your actual class and Q is your predicted class. Don't worry, I'll explain. Please focus now for now. Say you're dealing with a 4-class problem. Okay, you have 4 different types of images of animals. One animal class is lion, another is say ant, another is say elephant, another is say rabbit. Some animals randomly I'm taking one. So that means you already had your actual data in which you had your label and images. Someone has manually looked at your image and classified or given a label to that as lion. Someone has manually looked at all these images and gave different names to these images, and it's considered to be 100% accurate. That's the actual data. If it is 100% accurate, what that also means is if this is the image that is taken, since it's a lion, you will say, hey, there is 100% probability that it is lion, and rest of the things you'll say there is 0% probability that this is ant, there is 0% probability that this is elephant, there is 0% probability that this image is a rabbit, because it's a lion, it's actual data. Someone has actually given it to you. That's accurate data that they have given. Say using this historical data, you built a deep learning model. You use convolution neural network and then you built a deep learning model. Then the deep learning model for each of these classes, will give you some probability values. This is lion, ant, elephant, and rabbit. For each of these classes, it will give you some value. Say it gave you probability that there is 0.6% that this is lion, there is 0.2% probability that it is an ant, 0.1615 that it's an elephant, and 0.5 that it is rabbit. Overall, it will sum up to 1, because probability of all the values when you add, it will give you anyways 1. Now, Cross entropy is defined as summation of I equal to 1 until n, I mean how many ever classes you have, p into log of q, okay, minus. You have two classes, actual class distribution, probability distribution, and predicted class probability distribution is available. It's a 4-class problem. So how would you write it? Summation of I equal to 1 until 4, p into log of q. Same, exactly the same as entropy, right? So now you keep substituting I equal to 1 here, then you'll get uh, minus p1 into log of q1 minus p2 into log of q2 minus p3 into log of q3 minus p4 into log of q4. This is what you get. All right. Then you look at this. P1 is 1. So it'll be 1 into log of 0.6 minus 1 into log of 0.6 minus P2 is 0. 0 into anything is 0. 0 into log of 0.2 is 0. Then P3 is 0. So 0 into log of 0.15 will be 0. So if we were to choose this, this will become 0, this will become 0, and P4 is also 0, 0 into log of 0.05, sorry. This will also be 0. Okay, everything will become 0. So if all these three will become 0, then you'll be left with only this value. This will give you something, right? Minus 1 into log of 0.6. Not sure what is log of 0.6 base 2, but you might want to solve that. You'll get some value. That's called as your cross entropy or error, because it's not 100% with 100% accuracy saying that it is lion, this image is lion. It's saying you build a model using the historical data, you tested this image on that model, and it's giving 60% probability that it is lion, right? So you'll have some error, 40% error basically. Some error will come out of this. Now, let us imagine this. So let me first erase all of these things. Let me also erase these values. Say you built a model which was extremely good, and then your model, let me choose a different color. Okay, your model when you tested on this image gave you 1 here. That means it's 100%. I mean, it's predicting with 100% accuracy that this image is a lion. That means rest all you'll have anywhere zeros. Now let's look at this formula. Right, let's look at this formula once again. I need to erase this part also. Yep. So what would you get then? It'll be 1 into minus 1 into log of 1, because here q1 is 1, minus 0 into log of 0. This will become 0. P3 is 0 into this will become anyway 0 into log of 0. P4 is 0 into log of q4 is 0. You get 0. And log 1 is 0, so you get 0. That means there is no error. Entropy is 0. Why? Because with 100% accuracy, your model predicted that this image is a lion, and in reality also it happens to be a lion. So there is no error. You'll get entropy as 0. This is cross entropy. Now, this cross entropy is exactly equivalent to entropy value. When you calculate entropy, you'll get exactly the same value when both these P and Q are same. Both the actual class, actual values, and predicted values. If both of these are same, then cross entropy will be exactly equivalent to entropy. However, when P and Q are different, these two distributions are different, then what happens is cross entropy value that you get will be actually greater than entropy. Okay, by some number of bits. I think someone is writing on the screen. Did I give that access to you guys? No, right? Anyways, okay. If these two probabilities, actual values and predicted values, these two distributions are different, then cross entropy would be greater than entropy by certain number of bits. And those by certain number, by some value it will be greater, right? That some value by which cross entropy will be greater than entropy is called as relative entropy, or this is called as KL divergence. So next time when someone asks you in interview on what is KL divergence, or this is Kalman Lebler, Kal sorry Kalbach Lebler divergence. Right? If someone asks you what are these two, then this is the explanation that you need to provide. So that means cross entropy, if C is cross entropy, it is equivalent to nothing but entropy plus KL divergence. When is this formula going to hold true? When both the distributions of your actual and predicted classes are different. That is when this holds true. Okay, and the scale divergence is also another measure of error. It's also another measure of error, basically. In recurrent neural network and LSTM, etc., it's used. So it's denoted as divergence, scale divergence of P to Q is nothing but cross entropy of P and Q minus, I mean, you're just taking KL divergence, you're leaving it here, and entropy you're taking on that side, minus entropy of this. This is the ultimate formula for cross entropy or KL divergence, right? And cross entropy, entropy. This is how cross entropy, entropy, KL divergence, information gain, everything is interlinked. All right, I'll take your questions in a bit. But before that, we have this Jumpstart program. We have formally, tomorrow we are going to close this. People who enroll for this, for any of these programs, will get a special, I mean, on all these courses, we have slashed the prices by up to 90%. Students, you need to submit your ID proof, etc. For working professionals, there'll be a written exam, but tomorrow is the last day. And I request you all to share your reviews on our Facebook and LinkedIn. All the future webinars, etc., not just on the WhatsApp. A few interesting and important things we post it on Facebook and LinkedIn also, not on the WhatsApp groups, because it looks very spammy if we keep putting on WhatsApp group. Okay, now I'll take your questions. I saw a lot of questions. Guys, was my voice breaking in between? Okay. Muttu, underlying data in itself, your underlying data in itself has a lot of noise also, right? Because of that noise, by default, you'll have certain error. Okay, if I were to answer you, no, it's fine. Some saying, please repeat. Okay, when do we have to add weights? So, okay, money, we need to add weights. I'm sensing that your question is around this part. When do you add weights here? Here we added weights, right? 3 by 5 into 2 by 5. Why did we add weights there? Because when you look at the left hand side, which is less than or equal to 50, you add 3 entries only out of 5. So 3 by 5 into entropy of left plus. When you look at the right hand side, you add only 2. That means there is imbalance, right? 3 on one side, 2 on one side. Whenever you see such imbalances, you just do a weighted summation and then you get this. Okay. Any questions, friends, on this? So we covered a lot of ground, right? We discussed about basics of cost function, that's cost function or loss function or error function primer. Then we discussed on what are the various error measures which are available when output variable is continuous. Then we discussed about what if output variable is discrete with two categories. Then we didn't just stop there. We looked at for each class, positive class versus negative class, what are the various error measures which are available so that a model seems to be right balanced model. For that, we looked at precision, sensitivity, recall, hit rate, true positive rate, specificity or true negative rate, false positive rate, false negative rate, which is also called as alpha or type 1, beta or type 2. I mean, type 1, type 2 errors from hypothesis testing you can make out. Then you have F1 ratio, precision, recall. Then we looked at ROC curve. Interview questions could be something like this. Hey, what will you have on the y-axis and what will you have on the x-axis of ROC curve? Even TCS ION exam, um, I mean, same question was asked. And then we discussed about this multi-class discrete variable problem. Then we looked at how to calculate the cost of misclassification and how can we actually use that for sampling the data. Then finally we discussed about another form of error, that is entropy. And once you know entropy, you can also calculate information gain of each and every variable. Then we discussed about cross entropy. Of course, now you all would appreciate and you all would be aware of relative entropy, KL divergence, Kalman-Lebler, so on and so forth. So you have knowledge, showcase that, and all the best for your future and for your interviews. Let me take your questions. Vedika, I think I answered this. Um, yeah, it's coming up to zero money. It need not always be zero. In this scenario, it came out to be zero. Okay. Can we apply entropy on regression model? I don't think so. I don't think so. All right. And Money has a question. Is that correct? Yep. In this case, it turned out to be zero. I mean, this is what Money was speaking about, right? In this case, even when we'd have done a weighted calculation of entropy, we got zero. Yes, absolutely. Any other questions, friends? Please ask if you have any. If you don't have any, stay tuned to our YouTube channel. Next time it'll be live on YouTube as well as Facebook. And it will be for 4 hours. It will be one of its kind. It will brush up all of your high level understanding on how to handle data science projects end to end. All right, I'm going to stop here. Thank you all so much. And you guys, let me resume the recording also. We have come up with industry specific programs. You might want to check out our domain analytics site, HR analytics program, and life sciences healthcare, certification program in financial analytics, in marketing analytics. Then we also have social media web analytics, customer analytics. A few more things that we are adding to this kitty are uh, supply chain analytics and cyber security analytics. You'll be notified on the WhatsApp groups, right? For example, certified program in financial analytics will be for 40 hours. If you're wondering on what is covered, then all of these. Financial Analytics 101. What are the applications? Optimization and simulation primer. What would get covered? You just expand, we'll get to know. Risk return trade off and quadratic utility, optimal portfolio allocation, optimal risky portfolios, CAP model, Black Scholes and Monte Carlo pricing model, so on and so forth. And when it comes to uh, HR analytics, then these are the bunch of things. Modeling ethnic diversity, employee turnover prediction. How do you screen and select the right candidates? Team level and employee level engagement prediction. How do you conduct service and how do you predict employee performance? Sickness absence, especially in international flights, if your cabin crew calls you on at the last moment and says that, hey, I'm not keeping well, then you need to find another person who has a visa, because say that flight is traveling to US, right? Then benefits and compensation analytics, interventions and recruitment predictions, so on and so forth. Using videos, images, can you identify on whether a person is unhappy or not? One of your employees, can you do that? Yes, maybe. That's this thing all about. Yeah. All right, friends. Thank you all so much. Do stay in touch. Sure. Yeah, it's only used on classifications, just in case you want that. Thank you all. Bye. Have a great day.